Okay, so you've hopefully before you watch this video, you would have seen the earlier video or the video about high electric fields and the effect it has in like mobility digression and performance of short channel effects. So the essentially this paper is about a model. It's supposed to be a simple model for doing an analytic, um, basically hand calculations for doing, circuit estimations. For designs, you would want to use the computer-aided design models, but basically how to have a model that you can hand calculate, short channel device characteristics because they're not going to be have a simple model. So anyway, the way it sort of starts is by saying that, typically the Shockley model is used for doing analytic circuit calculation. So that's like a pretty simple model, and it's given here. I think we've shown it a couple of times in the class. Something you should be familiar with, the Shockley model. It's got the square law characteristics in the saturation region. It's got, a linear region, and it's got a cutoff region. Let me see if it's kind of like this fully the non-dashed curves is your Shockley model of the transistor. So it's saying that's typically used, but the Shockley model, it says, can't, deal with the short channel effect models. And most of that is caused by velocity saturation. Again, we have a lecture on velocity saturation, the high electric fields and stuff up. So I might want to take a look at that to brush up on the background. So basically, the idea here is they wanted to create a model that's used for an analytic expression. And what they mean by that is really just sort of hand calculation. So when you're doing design, you're going to use computer-aided design tools with the full up, really complex models. But the when you're doing hand calculations, those models are just going to be too complicated. A lot of them are numerical models. So you need something that gives you somewhere in between a Shockley level of simplicity, Shockley model level of simplicity, and something much more complicated. And also this model they're talking about using, there's also source and drain resistance is also included in this model, etc. So then they're basically start talking about this, um, the about the discrepancies between the simple model and the Shockley model and the small um, channel length models, and these are the saturation voltage is being different than the predicted value. Again, I think we talked about this. Let me see if there's a good. So for example, when you want to look at this, like the dashed line, the saturation voltage value is different than the predicted value. And the second one is that the drain current in the saturation region doesn't have a square law dependence. So again, we talked about this in the other video about velocity saturation. And if you guys aren't familiar with these nonlinearities, I suggest you might want to take a look at those. Okay. Um, let's see. So anyway, what these guys do is the upshot of the idea behind this is why the alpha model is it's kind of like a piecewise linear model, I guess is the best way to talk about it. Is that basically they're saying, let's say this is the actual model of the device. What they do is they create a sort of this piecewise linear model that's got a linear behavior before it hits the VD SAT. and then it has like a straight line for after you hit the after you get beyond VDSAT. So that's kind of the basis of the model, and it's really kind of getting into the details of this model. The I think what you end up with is you end up having a, let's see, where is that equation? Basically, this is kind of what you end up with is this relationship. Instead of this ID zero, you end up with this three regions still, okay? Where, well, first of all, what you do is you actually need to come up with this. This would normally be VD-SAT. So in the Shockley model, VD0 would kind of correspond to VD-SAT. But in this case, because VD-SAT is not what the Shockley model predicted, you need to have a kind of a more complicated equation for that VD-SAT. So that's the voltage you compare to figure out the drain source. Which region of the operation are you in this region, or are you in this region? Are you in this region or this region, etc. So you need to use this VD0 prime. And then ID0 prime after that is basically tells you, if you're in the triode region, the triode region is this case. Basically use this model and use this current value for it. And then in the so-called pentode region, you use the ID0 by itself as the value. So really kind of, the rest of it is talking about the details of why this curve fit is a good choice for the MOSFET and small order effects. So, but that's kind of the upshot of this thing is having these two very distinctly different regions. And this is not supposed to be really a exact model. It doesn't really do a good job of predicting the current, like kind of here you can tell it's not doing a really good job, but it does a good job at these endpoints. So this is basically one method of doing hand calculations. There was some of the interesting stuff that's in addition to that is talking about how, you need to use models to look at the slope of the input voltage changing compared to the output voltage changing. So a lot of times we assume that the input voltage is changing very, very quickly. So it would look like this. But really, the gate, your inverter, your NAND gate, whatever, is being driven by another gate. So that other gate is going to have its own rise and fall times. And those rise and fall times are probably going to be on the same order as the output of this gate. So basically, this kind of tells you that there's a whole kind of discussion here of how these rise and fall times affect the how you can basically model those in your hand calculations. And then it talks about the effects of source and drain resistance on the delay, which is kind of interesting. I think, like, as you'll see, the interesting thing about it is, to me, is that the source and the drain resistance have very, very different. Um, uh, so you think, the MOS transistor is symmetric, the NMOS. So if you have resistance on the source side, why wouldn't it have the same effect on the drain side? But it turns out resistance is much, much worse on the source than on the drain. And this kind of gives some reasons why and sort of a description of what happens. And so it sort of gives you a hint as to how to lay out your device to minimize the source resistance of your devices. All right, guys, I think that's all I had. There's some appendix here with some of the details, but the meat of the paper is, looking at how you can use this piecewise linear model to do, analytic calculations. Not, again, not for CAD, but not for the actual design. For that, you'd use CAD tools, but this would be for doing hand calculations.